Suppose that we are given two random variables x and y jointly distributed. If we are given the distribution of x comma y, then we can find probabilities of all sorts of events in terms of x and y, like these events. Now, observe that out of these, this one is somewhat peculiar in the sense it does not involve y. But when I said that you can work out probability of any event in terms of x and y, no one says that you have to use both x and y. You can use any one of them. In fact, you may not use any one of them either. So, if you know the distribution of x comma y, you can work out probabilities like these also of events involving only x, which means if we are given the distribution of xy, we can actually work out the distribution of x, namely probability of any event in terms of x alone, and similarly also the distribution of y. This is just common sense, and we have also seen this in our probability 1 class. Since in this case distribution is for two random variables, we naturally call it the joint distribution of xy, and it feels natural that we should also use some adjective to contrast with this, so we use the adjective marginal distribution of x and similarly marginal distribution of y. So even if I do not mention this joint and this marginals, it means the same thing, but just to distinguish that here you have got more than one and here you have got just one. It doesn't have to be one, it could be anything less than that. So we use the term marginal. We have seen the use of this term also in our Prob 1 class. Now we know that for any kind of distribution, one way of mathematically specifying that is by using the CDF. So in this case, we will call the CDF joint CDF, and similarly the CDF of x will be called the marginal CDF of x, and here marginal CDF of y. So there must be some way by which, given the joint CDF, you can work out the marginal CDFs, because given the distribution, you can find out these distributions. Here is a theorem to help us to do precisely that. First we are naming everything. X and y are two jointly distributed random variables whose joint CDF I call capital F, x, y as usual, and x and y, they are also random variables, so they have their own distributions, CDFs. So those CDFs, which are the marginal CDFs, I have called them fxx, fyy, because CDFs always exist. I want to find out these two given this fellow. So I need some way of arriving to this from this. The technique is this. You take fxy. Now x, you are trying to find out this. We will see how to find this in a similar way. So someone has given you a little x and you want to compute this f subscript capital X at that point little x. You put that x inside this capital F and you put some y there. You let this y go to infinity. This limit is bound to exist, which is obvious because this is a non-decreasing function. It is bounded from above by 1, so the limit has to exist, and that limit will be precisely what you are looking for. Now, why is that true? That is pretty straightforward to see. This thing is by definition probability of this event. Similarly, this thing equals this probability. Now consider these two events. This event is precisely this infinite rectangle, probability of that. Now as you are letting y increase, it is going up, 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 until as y goes to infinity, it just becomes the total half plane to the left of this vertical line, and that is precisely this. So all these events increase to this event, and therefore by continuity of probability these things must increase to this probability. So the limit of this equals that. So mathematically, since these events increase to this event as y goes to infinity or y increases to infinity, therefore this probability must converge to this, which means this thing, when you take limit, you get this. Obviously, you can have an analogous result to compute fyy. The proof of this is absolutely similar. This result is perfectly general. It holds for all sorts of random variables because every random variable has its CTF. But if we further know that there is a density, joint density, then we can also conclude that x and y also will have their own densities, the marginal densities, that also you can compute. This theorem is very much like the last theorem, except that we are working with joint density. So it is not a general theorem. It works only when there is a joint density. Our aim is to find out the marginal densities of x and y. Then a marginal density of x is given by this thing. You are integrating out over the variable that you are not interested in. The proof is absolutely straightforward. In order to show that this is a density of x, we have to check that for any a less than or equal to b, this probability is given by this integral. That was the definition of density. So you just take any such a and b and then you write it down as an event involving both x and y. Now this additional thing that I added is actually no condition at all because y is some random variable. It takes values in R, so it has to lie between minus infinity and plus infinity. So these two things are actually the same. But now that I have written it in the form x is in some interval, y is in some interval, I can use the joint density and integrate with respect to y from minus infinity to plus infinity and with respect to x from a to b. We have already mentioned that the order of the integrals does not matter, so we have done it in this way. Now I quickly recognize that this fellow is precisely this fellow. So this is same as, and that completes the proof. And similarly, if you are interested in a marginal density of y, you integrate out the unnecessary variable x from minus infinity to plus infinity. In this problem, we are starting with a trivariate distribution because we have got three jointly distributed random variables with joint density given by f, x, y, z. Your job is to express the joint density of x, z only. So this is also a marginal obtained from this because it's a subset. I had 3, now I have got only 2. I have eliminated y. You have to find the joint density of xz in terms of f, x, y, z. That is part 1. You have to do it in general using integration of this. Now in the second part, you have to use the formula you obtain here to this particular joint density.